Have you ever watched a robot move and just wondered what's really happening inside its head? And I don't mean the gears and the wires. I mean the ghost in the machine, that invisible, silent conversation that's happening thousands of times a second. Well, today, we're going to learn how to listen in. We are decoding its secret language.
I want you to picture a factory robot. It's just a blur of precision, right? Its camera sees a part, its arm grabs it, and its base moves it. Now, hundreds of messages are flying between those parts every single second, but somehow they all move with a single, flawless purpose. So what is it? What's the invisible force that's conducting this whole mechanical orchestra?
Well, the secret lies in a blueprint, just like this one. Now, it might look pretty simple, but trust me, this is the key to everything. This is the journey we're going to take today, and we'll keep coming back to this map as we uncover each piece of the puzzle.
So what is this invisible conductor? The language our blueprint is written in is called ROS2. That's the Robot Operating System. You can think of it as the ghost in the machine, the framework that lets a robot's eyes, its arms, and its wheels all speak the same language.
The best way to think about it is like a biological nervous system. You see, ROS2 provides the pathways for, say, a tiny sensor on a fingertip to talk to a really powerful motor in an arm. And that right there, that's the secret superpower for anyone building a robot, getting all those different parts to work together as one.
All right, let's start breaking down our map. We're going to start with those shapes at either end. These are the fundamental building blocks of any ROS2 system. These are basically the robot's digital brains.
Now, in ROS lingo, these brains are called nodes. A node is really just a single program, a process with one very specific job. So one node might handle the camera, another one controls a wheel motor, and maybe a third is busy calculating the path. Each one is a specialist.
And right here, you're actually seeing one of these digital brains come to life. This is a terminal running a single ROS2 node called /talker. And its entire job, its whole purpose in life, is to shout a message into the void over and over again. Hello world 1, hello world 2, just a constant broadcast.
So we've got these digital brains, right? But a brain that can't communicate is, well, it's pretty useless. So how do they actually talk to each other? Let's look back at our map and focus on that arrow, the connection between the brains.
That connection is called a topic. So if a node is the brain, then a topic is the nerve pathway. It's really just a named channel, kind of like a radio station, that a node can broadcast data on. And then any other node can tune into that specific station to hear the message.
And here it is, that radio broadcast in action. You can see up top, our talker node is sending out its hello world message. And then right below it, a second node, the listener, is tuned into that exact same channel. And look at that. It's catching every single message the talker sends. It's a perfect connection.
And just like that, our blueprint is decoded. See, it's not a mystery anymore. We have the talker node, that's the brain, sending messages over the chatter topic, that's our nerve pathway, and it's being heard by the listener node. This simple pattern, this is the absolute heart of communication in the entire world of robotics.
Okay, so we understand the language now. But to really master it, you need a place to practice. And let's be real, you probably don't want to practice on $1 million robot arm. So what if you could build a perfect, totally disposable virtual lab right on your computer to experiment in safely? Well, that's exactly what a technology called Docker lets us do.
A Docker container is essentially a lightweight, portable box that holds your application and everything it could possibly need to run, all the libraries, all the dependencies, the whole shebang. It completely isolates your robot's code in a clean, safe sandbox so you can build and test without messing up your main operating system.
And creating this lab is a really simple three-step process. First, you build your custom environment, which we call an image. Second, you run your programs inside containers that are based on that image. And third, you see the results. Let's walk through it real quick.
So step 1 is all about the recipe. We use a simple text file called the Docker file, and it lists every single ingredient our virtual lab needs. Then we run one command, docker build, and it just follows that recipe to construct a perfect, reusable image of our lab.
Now for step 2. We launch our lab.
And check this out. Our talker and listener nodes are back, but this time they're running inside separate, totally isolated virtual boxes. And even though they're completely walled off from each other, they can still communicate perfectly. This is the power of a ROS2 network.
But can this lab handle the heavy stuff, like complex graphics? Absolutely. What you're looking at here is RViz, a really sophisticated 3D visualization tool for robots, and it's running flawlessly from inside our little virtual lab. This just proves we can build and test almost anything in this safe, portable environment.
All right, we've seen the theory. We have built the lab. Now it's time for the climax. Let's put everything we've just learned together and give a direct command to a virtual robot.
I want you to meet TurtleSim. It's a super simple 2D robot simulator, and it's perfect for our first experiment. As you can see, there's just one lonely little turtle in the middle of its world. So let's give it a friend.
This command, this is our magic spell. And with it, we're using a new form of communication. Instead of broadcasting on a topic for everyone to hear, we're calling a service. This isn't a radio show, it's a direct phone call. We're calling the /spawn service and giving it a single direct order. Create a new turtle, name it Turtle5, and put it at coordinates 2, 2.
And boom, a second turtle appears, exactly where we commanded it to. We sent a request, and the simulator sent back a response. Success! This direct request and reply, it's another incredibly powerful way for robot brains to talk to each other.
And so, we come back to our blueprint one last time. It's not a mystery anymore, is it? We understand the nodes, the digital brains. We get the topics. Those are the pathways for broadcasting messages. And we've just seen a glimpse of services, the direct phone lines for specific commands. The secret language is officially decoded.
So we've seen how robots talk and how they take single commands, but what happens when a task isn't instant? Something like navigate to the kitchen, which could take minutes and might succeed, or it might fail. How do they handle that? Well, that's a completely different kind of conversation, and that is our next story.
Hari!